All right, first online lesson. 3.3 heating curves. Now, so far we've seen energy diagrams with chemical reactions where we plotted potential energy on the y-axis and time on the x-axis. This one is a little different, and it's important that as we go on here that we don't confuse the two curves. Heating curves are done with physical changes because we are interested in a physical change as we heat a solid to liquid to gas. Okay. Now for a heating curve, the y-axis is temperature. Now temperature is something that we've felt and have used in our daily lives. In science, temperature is actually defined as the average kinetic energy. Okay. And kinetic energy is something that we are familiar with. It is the energy a particle possesses due to its motion. So if something is moving a lot, then we say that it has a high kinetic energy. Now, on Tuesday, we did a lab, and I had you predict what you thought the heating curve of a compound paired dichlorobenzene would look like. And a lot of you gave me fairly good predictions. A lot of you said it might go up and then taper off. Some of you said linear line, and some of you said, I don't think anybody said that one. That's ridiculous. But a lot of you were very on point with that first guess, okay? And so if you had a chance to graph your results, you might have seen that the curve has plateaus in it, okay? Quite a few plateaus. All right. Let's do an example in our notes. This is a heating curve of chemical X. It doesn't matter what chemical X is. I will just give you the general profile of what the curve looks like. Okay. Let's pretend that at time 0, we're beginning at 10 degrees. And what should happen as we heat the substance up? Well, it should be a no-brainer that for a solid, if we're starting with a solid, that is, as you start to heat something up, isn't this fancy? The molecules start to move a bit faster because you're giving them more energy. And if they are moving a bit faster, okay, a little faster, the more energy, that should mean that its temperature should increase because, once again, temperature is the average kinetic energy of a substance. So let's start the curve here. As we heat up the substance, we should see an increase as the molecules gain more and more energy. Then what happened in your lab is that you discovered that at some point when the substance begins to melt down or change phases, the temperature actually holds steady. It holds steady for a very long time. And most of you found that that temperature was somewhere between the 50s, 53 to 56, somewhere there. Okay? And I'll explain that in a minute. Once you got past the melting point, though, once you figured out that all the substances melted in your lab on Tuesday, you saw that the temperature began to rise again very sharply, and I had you stop at 70 degrees. Okay. Now, I hope from this little animation here, little simulation, that it makes sense to you that as you increase heat, the temperature increases, or the average kinetic energy increases. Okay. So going back to our notes here. We are going to draw, oops, it's quite hard on the tablet here, a tapering, and then another rise. Now we didn't do the second plateau, but if I had you heat the paired dichlorobenzene up forever and ever, and let's assume that you had unlimited sources of energy and you managed to heat that up way above the hundreds, you would have seen a second plateau to indicate the second phase shift. Okay. Let's put some labels in. In any substance, if you start with a solid and you start heating up, the slanty part, the very slanty part of the curve is where the substance is 100% in solid phase. This is where the energy that you input into the system is being used to increase the kinetic energy of the substance or the particles. So this is where the particles are vibrating beforehand as a solid, and now they're vibrating a little bit more because they're trying to break free of those intermolecular bonds that are holding them together to be a solid. Okay. Now the plateau is where we have a phase transition. This is where our solid is transitioning into a liquid. Okay? And when substances do that, when they undergo a phase change, the temperature we find actually starts to plateau out. Now, why is that? It turns out that when the substance is changing phase, the intermolecular bonds that are holding the substance particles together are being broken at that point. And as we learned from the previous unit, whenever you're trying to break a bond, whether it be intermolecular or intramolecular, you have to input energy. So, in the beginning of the curve, I'm just going to call this section A, the curve. In section A, the kinetic energy is increasing because you put in more heat into the system, the molecules are shaking, moving a bit more, and so the kinetic energy increases, so the temperature increases. At a certain point, the substance can't take it anymore. The intermolecular bonds are being stretched so far that they're starting to break. And at this point, we're going to call that section B, all the energy that you have given to the system is being utilized to break those intermolecular bonds. One could say that the substance is absorbing the heat to use in breaking their intermolecular bonds. And this is where the substance is starting to change phase. This is where you saw in your test tube that there was both solid and liquid phases present at the same time. So the particles in section B are not moving faster, they're not getting more kinetic energy, because all the energy that you've given it is being used to break intermolecular bonds. Now, once all the intermolecular bonds have broken, then all the energy that you give the system is once again utilized to increase the particle's kinetic energy. And so this is where, again, I'm going to call this part C here, this is where the particles are to increase their movement, and so kinetic energy increases, and we see that as a temperature spike when we're measuring the temperature of our substance. Okay, so in our second spike here, okay, this is where the substance is 100% in liquid phase. And then we follow a pattern. The next plateau that we hit, this is where the substance is shifting from liquid into gas. Okay, we'll call that section D of the graph. Okay, so section D, much like section B, we have a tapering of the heat curve, and this is because all the energy that you've inputted into the system when you're heating the substance is being utilized or absorbed by the substance to break its internal intermolecular bonds. And because it's using the energy for that purpose, the energy is not being used to speed up the particles. You can think of another way. These particles are held together very tightly as a solid. They begin to vibrate. At a certain point, they can't move any more than they already are, unless you break the intermolecular bonds holding them together. And so this is why we have a plateauing in the energy before we continue in the spike in the increase, because we kind of have to cut loose the bonds holding them together first before they can actually increase their movement or the kinetic energy. Okay? And lastly, in part E, we have the substance as 100% gas. And this is a very typical heating curve of any chemical compound. We have plateaus where we have 100% of one phase, and we have slopes where we have 100% of one phase, and we have plateaus that indicate the phase change. Okay, couple of points on this graph to take note. If you are given a heating curve of a chemical compound, you should be able to read what the melting point of that substance is. In this case, all we have to do is look at where the plateaus are located, and this point right here, that is what we call the melting point. And for this curve that we have drawn, roughly 50 degrees Celsius. Okay, so that is the melting point. Then we have another special point right here. This is the liquid to gas, roughly right here. What does that look like to you? Maybe 95 degrees, perhaps? What do we call that one? Hopefully in your heads you're going, it's called boiling point. And you will be correct. Okay? This is called the boiling point of a substance. And for this particular curve that we have drawn, that looks to be about 95 degrees Celsius. If you didn't draw the curve exactly like I did, no problem. Just read whatever melting point and boiling point that you have drawn and label that onto your diagram. Alright, so I have summarized some points down below. So parts ACE, this is where kinetic energy is increasing. The distance between particles begin to increase. We have a bit more movement. However, the intermolecular bonds are still intact. Okay. You can write a note for yourself. Perhaps point number 3, intermolecular bonds are still intact in these points. Okay. And of course, in these sections, we have 100% of one phase, not a mixture, because the intermolecular bonds are still intact. In sections B and D, where we have the plateaus, the substance is absorbing heat to break the said intermolecular bonds. Okay, all the heat is being used to break these bonds, so temperature stays constant. When intermolecular bonds are broken, then we get a phase change. Just realize this thing's on my screen. Okay, so why do we talk about this concept? Well, it turns out that when you know the melting point and boiling point of substances, it's very useful, very useful. Now, remember how I said one of the goals of chemistry is when that after you synthesize a compound, you kind of have to make sure that you've actually synthesized a compound that you intended. And this is where we talked about separations and isolating techniques and identification techniques. So one of the techniques we can use to identify whether we have a substance that we meant to make and whether if it's pure or not is that we can cross-reference the melting point of our substance against the melting point in literature. Okay, what I mean is this. Pure substances, okay, any pure substance, it will always undergo phase changes at fixed temperatures, just like you know that water boils always at 100 degrees Celsius. If it didn't boil at 100 degrees Celsius, you probably have water with other things dissolved in it. Okay, so let me give you a story here. I am a chemical company. I want to produce paradichlorobenzene. I just figured out a way to synthesize that compound. I've separated it out. I've isolated. Now I need to check that I've actually done a good job and that it's actually pure enough for me to use in industry. What do? I take my substance, put it into a little apparatus we call a melt temp, which is something that heats up a substance and we observe when it melts. I check the temperature, looks like it melts at 40 degrees. I look at Google. Google says it should melt in the 50s. Darn. My sample must have been contaminated with something else. Okay? Pure substances will always undergo phase changes in fixed temperatures. In standard conditions. There's always a little fine print. Sometimes boiling points can be different for pure substances depending on where you are doing the test. For example, water at sea level will boil at a different temperature, slightly different temperature, than if you were to boil it up on a mountain. Okay? But melting temperature is fairly constant. Where you go, boiling temperature tends to be a little more variant just because air pressure can influence that. But melting temperatures are usually pretty good. Okay? Alright, on the bottom here, just a few vocabulary words. Melting point, freezing point, boiling point, condensation temperature. Just be aware of those words. You should be familiar with these as we've gone over what the words are for each phase change. Okay. Now, just as we end here, here is a little thought. What if we were to draw the cooling curve of chemical X? What would that look like? We shall investigate that in class on Thursday, and make sure you copy this down, and I'll give you some practice multiple choice questions on Thursday regarding this topic, and we shall see how many of you understood this concept from this very lively, very animated, entertaining online lecture series, episode 1. Go out!